Good, very good. So, welcome here. My name is Petr Svenda, and together with my colleagues Vladimir Sedlacek and Jancar, we prepared a paper about how to test primality testing on devices where you don't have the source code, so you don't see what's inside, and still you would like to get the test whether the card or proprietary library is testing prime numbers properly. We are all from the Masaryk University in Brno, Czech Republic, and Vladimir Sedlacek is also from Foscari University, Venice in Italy. Good, so some motivation. We all know that some parameters in Diffie-Hellman or digital signature algorithm and their elliptic curve versions needs to be prime. And if they are not, and you will start computing over the curve where some domain parameter is not a prime, frequently you can extract the private key. So the attacker can get the private key. And this is well known thanks to Polik and Hellman. They published in 1978 the attack and show how this can be done. So now we know that we must have certain domain parameters to be a prime. So how to achieve this? There is one option to construct the numbers to be provable primes. So we will construct them that for sure they are primes. But this construction is time-consuming, and especially in limited devices, that's difficult. So another option is to utilize some probabilistic primality testing algorithms like Miller-Rabin. And it's probabilistic, which means it can't prove that the number is prime. And there is always a tiny chance that the number is composite, despite the fact that this algorithm accepted it as probable prime. And these false negatives are called pseudoprimes. And if you know what are the particular parameterizations of, say, Miller-Rabin algorithm, you can construct numbers that are these pseudo-primes. So they are composite, but looks like a prime for these algorithms. Already known from 1995. And it was shown that in a practice, many implementations of Miller-Rabin algorithm can be fooled. In 2008, thanks to Daniel Bleichenbacher, he shown that there is issue with GNU crypto, and more recently, in 2018, by a group of authors, that a lot of open source libraries do have issues with primality testing. So basically, you can craft the number, and it will pass the primality testing. And if then that such number is used in computation, thanks to Polik Hellman, you can get the private key. So serious issue. So how we can continue and fool randomness test? So we will first take the implementation of Rabin-Miller algorithm, look into the source code, and obtain the parameterization. That parameterization is called witnesses or bases, used in every round. And then with the knowledge of this, we can start creating these pseudoprimes. And Daniel Bleichenbacher in 2008 basically looked into the code of GNU crypto, figure out they are using only the first 13 primes, and then crafted the pseudoprimes that will pass the tests using this as a basis or witnesses. So there is a method for that by Arnold, and then you do have the number which is composite, but will pass this algorithm, and you will submit this to primality verification of the target primality testing, and if accepted, you can then start do factorization or discrete logarithm due to the composite parameter. There are some differences well known. Miller-Rabin as such is not bad. It just needs to be used and implemented properly. So if you will implement it with a random basis, then you are fine, very likely. And there are also other primality tests like Bailey, PSV primality tests. So we know both issue, the problem, as well as how to fix that. So the question is there anything more to research here? We can just like take all existing implementations, look at the source code, figure out whether they are doing this right. If yes, then they are okay. If no, then we will issue the fix. That works well for white box implementations where we do have source code. But the question is what we can do with the black box ones. If there is a black box device like smart card and we don't know the source code, we don't know how they are implementing parallel mirror inside, or it's some proprietary library. So in this case, we don't know, and this is what our paper is about. So a little bit about cryptographic smart cards. Smart cards are small computer built for security. It has small attack surface, small trusted computing base in hope that it will be more secure, and it's frequently certified. So if you will look at common criteria certification, 38% of currently active common criteria certificates are related to smart cards or programs running on the smart cards. And they are also frequently certified to high levels. So it's not just like some self-assessment claims, they are really certified to level 4, 5 plus, and even 6 plus, which means it's semi-formal, analyzed, and certain properties are shown to be correct. With these smart cards, if you are a developer and you like to develop something on top of it, Java card is currently the dominant open platforms for cryptographic smart cards. It works so that you first have the layer which is the smart card hardware. On top of it, you have vendor-specific operating system. Then you have Java card virtual machine, pretty much the same as standard Java virtual machine you know from your computer. And this is all vendor specific. But on top of that, by Java card forum, there is a public API specified, and applets, which are applications running on cards, are using this public API. And because they are using something that is common over the cards from different vendors, you have some portability among these cards, and that was the idea why it was introduced. So, for example, if you like to do digital signatures, you first need to generate key pair, and before that, if you are using elliptic crypto, then you need to set the parameters of the curves used. So you have a bunch of public methods, you will set these parameters, and then you will call key generation, and you can start signing. The API specification is public, but the methods itself are still implemented by a specific card vendor, and we don't have the source code for this implementation. So this is the black box scenario I'm talking about, and primality testing is implemented somewhere inside. So it's hidden inside, but we don't have the source code. So we have two main questions here to investigate. So first one is whether the primality testing is correctly implemented. Possibly they are using Miller-Rabin with some fixed basis, and maybe we can construct pseudo-primes for that. Second question is the primality testing really used where it should be? Because it's no good if we will have the very robust primality testing, but we will not use that functionality where it matters. So if it's missing test, it may lead into private key recovery. So we for sure know that the primality must be implemented on the smart cards, because smart cards are capable to do RSA key pair generation, and for that you definitely need primality testing. But there is no method with the name something like isPrime in a public Java card API. So we don't have in a public API method where we can just send the number and it will tell us whether it's prime or not. Would this be a case, then we would have like easy and straightforward path towards the testing of whether everything is implemented correctly or not. But it's not there. So the idea we figure out and made it into practice is we must somehow trigger the primality testing indirectly. We don't have the direct method, we must do it indirectly. So we need to find a public method that can be called directly by us, which inside will require some test for primality. It will then call some internal isPrime method, and we will then get the result. Maybe rejection because it's not a prime, maybe okay because it's prime. One example might be setting the parameters of the curve. So we do have the method called setFieldFP, which is setting the cardinality of a base field for the curve. So we can call it and call it with a number which is not a prime, which is pseudo-prime, so it's some kind of composite. And then we can expect error. And if there is error, okay, likely they detected that we submitted something that is not a prime. But there is a problem. Card can reject the parameters we are submitting, this pseudo-prime, also for other reasons than not being a prime, because we are no longer testing just one number and calling method, hey, tell us whether this is prime or not. What we are doing is that we are setting some complex domain parameters, not just one, but a bunch of them, and then we are doing some operation with the result. So it can be rejected just for also for the reason, say, it's too long. So maybe they are not checking properly, but they will reject our pseudo-prime anyway, but for the different reason. And this would result in false negatives in our case. So we will think that it's testing properly, but it's not in fact. So what are our contributions? So we did the methodology, how to test primality on black box devices, how to assess whether they are doing it properly or not, despite not having the access to source code. And this required some new methods for generation of Diffie-Hellman and digital signature algorithm compliant composite numbers and pseudo-primes, because we need to set the whole all domain parameters of the elliptic curve, say. We are testing 4 different scenarios. One are for standard Diffie-Hellman and DSA, and remaining 2 are for elliptic curve versions of these. And for all of them, we tested various numbers of factors for these composite numbers, smoothness level, and of course bit sizes, because different curves are supported, different length of curves are supported by the smart card. So we need to test them all. And for the first 3, there are already known attacks, so you can just directly apply known attacks. But if you will start doing computation with P not being prime in ECDSA, for example, then there was no known attack, so we developed one. If you are interested in details, just look into the paper. Basically, we reduce the discrete logarithm problem over a big curve, which is hard to compute, to easier discrete logarithm problems over the small curves. And it's via some elliptic curve version of Chinese remainder theory. And equipped with this, we went and checked this idea and this methodology on smart cards from major vendors. And we also open sourced the testing toolkit, so you can just grab it and test on your cards or on your white box implementation, if you wish. So now I will mostly talk about these 2 points. So how the basic setup looks like. So we first need to construct pseudo-primes and other composites for this. That's relatively easy, well-known methods for that pretty fast. Then we need to generate proper parameters, the other domain parameters for this. This really depends on which scenario we are targeting. It can take seconds to minutes, but sometimes it's quite time expensive, so it's like weeks of pre-computation. Then equipped with already a number which is the valid domain parameter, except it's not a prime, so it's not a valid parameter, but everything else is proper. We can start triggering the primality testing, but indirectly via set field fp, and maybe then calling key generation method. The issue here is we need to not just set the domain parameters, we also need to generate a key pair, sign something, maybe verify it, because we don't know where exactly they are testing for primality. So we need to do the whole chain. And then we are observing the resulting behavior. We will look what is the error returned by the card, what was the response time, how long the card computed something, whether we got a muted card, and so on. And because we are dealing with the real devices, so there can be some non-deterministic behavior, as well as some configurations can be more rare to occur. So we basically run every experiment 100 times with different inputs, and each input was repeated 10 times to capture non-deterministic behavior. And of course, when we were successful, we also verified that it really works and we can compute back the private key. So, some results. On the left, you can see the cards we tested and the methods we tested, just snippet of that, more in the paper. And if you will set the expected correct parameters that are primes, all cards will just return OK, which is expected. Like it's the regular situation with correct parameters. But if we will start to fiddle with that, instead of prime, we will send pseudo prime, or we will set some pretty basic composite out of 3 factors or 10 factors and some smoothness. We will start to get interesting results. How to interpret this table? If it's green, this means the card correctly accepted or rejected as expected, like from the defender's point of view. If it's red, then it means that the card accepted the input despite being composite. And then if carried the computation, attacker would be able to get the private key. So that's the red. If it's yellow, then this means card seems to accept the arguments, but before being able to produce the final signatures that is necessary for an attacker to extract the private key back, it somehow got stuck, either with some non-standard exception, or it muted, or cycled, and so on. Now, how to interpret different codes. IL means illegal value, and that's desired error, because we are giving it illegal number, so it shall be rejected. If you will see OK, and it's red, this means we submitted the composite number, and it was completely accepted by the card, and at the end, the card gave us the signature, and we were able to retrieve the private key. And if you will see something like cycling or exception or muted, this means the card did something and got stuck. Likely, the reason is that the card accepted the value, but the algorithm later on implementing the necessary operation on, say, elliptic curve had some expectation that some things will hold, and because we submitted something that is not a prime, it broke, and then the card cycled, muted, through some strange exception, and so on. Okay, so you can see that most of the cards had an issue, and we believe that most of the cards are not checking primality at all. So it's not that they are using some weak implementation of Rabin-Miller, they are not checking at all. We disclosed this responsibility to affected vendors during the last year, and just to summarize, There seems to be only exception one card that is doing the testing properly, Athena ID Protect. There were cards that were just happily accepting the composite numbers, then computing, and we were able later on get the private key, so that's bad. And there were some cards that were in the middle, that we think that they are doing some primality testing, but insufficient one. So how to fix this issue? So there are some obstacles. First of all, the code doing the implementation of primality testing and doing the checking of curve parameters is burnt in ROM. So for cards that are already deployed, frequently you can't update it. So you may say, okay, I can't update the code, but I can additionally check in my own applet code before I will provide the values to the card. But unfortunately, you can't really do so, because there is no sprime method in API, and implementing the whole Rabin-Miller on the level of Java card virtual machine, that would be too slow. So at the end, you can't really check, and you must trust the supplier of the parameters. And this is basically removing one possible layer of defense. So the impact, where is it relevant? So the attacker will win only if the attacker will manage to convince the card to set the parameters for, say, domain parameters for the curve, and then do the ECDSA computation and output the signature. Okay. There are some protocols and formats that allows to set explicitly the domain parameters. So for example, TLS up to version 1.2 was allowed to explicitly set domain parameters. X509 certificates also allows to public keys to be accompanied with full domain parameters. And electronic passports are also allowing to transmit this during the negotiation between the passport and the border terminal. And another issue that might happen is, of course, fault induction. So if the attacker is able to do some bit flips on the buffer holding the domain parameters, then these parameters are then used. But that's different use case scenario. We were focusing on a different one. So what are the recommendations? Just do what is already specified in various standards, like ANSI X9.62. So just do the full domain parameter validations, including these primality tests. If you are doing primality tests, then do it properly. So either use Miller-Rabin with random basis, or maybe Bailey PSV shall be doable on the card as well. This is not really mitigation, but it's like way around. If you will not allow attacker to set the domain parameters, then attacker of course can set the invalid ones. So there is an option to initialize your digital signature algorithm with named curve. This is already part of Java card 3.1 specification. Unfortunately, my guess is it will take at least 3 years before we will start seeing the cards with that level of specification, because currently some cards do have 3.0.5, which was released in 2015. So it will take long. Another option would be to add primality test to public API. So something like Sprime. Again, it seems to be hinted by Java card 3.1, but it's not a direct test. You can just say, I would like to use Miller-Rabin during the primality testing, but it's not allowing you to set directly the value. So finally, the conclusions. It's well known that primality testing based on Miller-Rabin algorithm, if not implemented correctly, can be fooled. And we proposed new method how to test the primality testing in case you can't directly call the primality testing functionality. You need to do it via some intermediate functionality, in our case, setting the domain parameters for, say, elliptic curve Diffie-Hellman, and this requires to have a bunch of different domain parameters to be consistent. And the result on current smart card is that it's mostly not used, and as a result, the cards are vulnerable to this kind of attack. It's hard to fix, so we need to trust the supplier of algorithms, and the recommendation is just perform the proper domain validation. Everyone can download the source code and already pre-computed domain parameters, so it's now easy to test also for the black box devices. And that's all from my side. I'm happy to take questions. Thank you.